My name is Marijn Daniels. I'm a technology guy. I'm not an archivist, I'm sorry. But I love working with archivists. I love people with passion, and that's what I found in the VRT archive. So, I'm at VRT since 2001. VRT is my first and only employer, so that's a good thing. So I'm responsible for all the technology used in the archive. So my team is responsible for the MMC system, for the integrations, the AI projects we do. So the entire spider web around the archive is my domain. Something about VRT for those who don't know. So VRT is the Flemish public broadcaster. As you know, Belgium is split up in different federations. So the Flemish part is the northern part, speaking Dutch. We have 3 TV channels, 5 radio channels, and the reason why I am here today is because we have an issue with growing digital touchpoints and growing volume of content being produced. Some numbers about our archive system. So we have about 7 million objects in our archive. It's about 18 petabytes times 3. So we obey the 3-to-1 rule as well. And we see a growing volume of 1.5 petabyte per year. Well, about 2.25 million video objects, 2.17 music objects, about 600K audio items, 1.25 photos, and about 60,000 film reels we manage. And the topic of today is AI. So at VRT we're looking at AI for a few years now. So we started with speech. The first implementation was for our subtitling department. So re-speak to text. The second project was speech transcriptions. So we had a tender out for that and have a solution in production for the moment. But when planning our AI roadmap, we take into account 2 things. The first thing is, I guess for all of you, budget constraints and the number of hands available constraints as well. For us also. So we look at how can AI help automating the manual tasks. That's the first parameter we use. And the second one is data value. So how can AI help us generate more value with our data? And so speech was the first one. The second project we did was automatic segmentation of content. And the colleagues of INA will take that topic in half an hour. And now we're looking at, as Karen said, my topic for today is speaker labeling. So what did we do? We looked at our content and checked from where can we extract our speaker labels. And as you know, in production, there's already data entered in different systems. So, for example, if there's an interview on the bottom of the screen, the name of the person is shown. And that's what we call the lower thirds, because mostly they're positioned in the lower third part of the screen. But in fact, it's just a textual source of data. And mostly, there's an example here. I can show some other examples. Like in sports, an interview with the future winner of the Giro. But also in live sports coverage, a getaway group, the different riders in the group are mentioned on screen. Or Prime Minister, experts in a studio environment, but also in documentaries we have produced, the different speakers are labeled. And as you see by these examples, well, they're all in a different form, and that's the challenge. So, for example, now there's our Queen Elizabeth contest going on. It's alternating between singing and playing violin. So this is an image from last episode. So these are just some examples of speaker labeling. And the challenge was from how can we get the data out of the picture. But the most important question, and for those of you who have young children, the most important question is always why. So why do we need these speaker labeling into data into our system? And as I said, the most important factor is value. And we just took a look at our systems. What do our end users do? What do they search? And the majority of the searches are on person names, apart from dates, program titles, events, keywords, but person names are always on top of this statistic. So the question why, the goal is to increase our searchability. So, but as I said in these examples, in production, the data is entered by humans. So they see a getaway group in the cycling race and they enter the names of the riders, and so the data is entered somewhere. So why do we need a solution to get it out of the picture again? Well, it's human error or lack of integration possibilities with systems, or even for internally produced content, we're not able to get the data out of the systems. So that's why we look at AI to help us in that. But in the past, it was all done by hand. So our archivists, every program, every content was rewatched, re-listened, and speaker names were entered manually into the system. But as I said, the challenge is the growing number of touch points, growing number of content to be annotated. We have just too little hands to handle all this content, so we'll have a need for automation. So the question of my toddler is answered. Now, a grown-up question, how did we do it? So, we used different techniques. So some of them have already passed the review here. So we used optical character recognition. OCR has been around since the 60s, in fact, with a great breakthrough in '74. So it's not new or innovative technology, but is the application on images, video, that is quite innovative. So yeah, we extract textual characters out of our images, and that's how does it work? It's just based on pattern analysis. In any language, different characters are written in a certain pattern, and we have algorithms who can recognize these patterns. But then you have text characters. You don't have words, and you don't have person names yet. So you need some form of interpretation of these character sequences. And that's where natural language processing comes in, and named entity recognition. Yeah. We also took a look at another way of doing it, because this looks quite complicated. Why not use the graphics system? So these lower thirds are computer-generated graphics. So why not train a model to recognize these graphics and get the data from that? But I don't know how it is at your organizations, but in our house, graphics change all the time. We get a new CEO, we get a new logo, we get a new graphics. So we did it with OCR and natural language processing. One technical slide. So that's how we did it. So it starts from our MAM system. In our case, it's Avid Interplay MAM. 2 triggers. We have some automation in place. For some programs, we know there are lower thirds in place, so we just automate it on ingest. The transformation is triggered. Or a manual way, an archivist can decide this piece of content is likely to have lower thirds. I'll send it to the algorithm. Well, as you see, we used AWS, a clustered environment for performance reasons, parallelization of computing. So the video is sent to the cloud, to the cluster, split up in little blocks to have them transformed in parallel. We take the characters out, we make words out of it, and then we try to filter out names. That's in short the way we did it. And the result is sent back to the MAM system to the user. Yeah. So to sum up, this is the flow. So it gets uploaded, split up. Based on cost, we don't inspect every frame. That's too costly. So we just take a frame each second. So we have a 25 per frame second video. We just take one of them and inspect them. I'll show an example of the grouping we did, because sometimes a name is written on different lines or something like that. So we have a grouping in place. And then another example, because the OCR is quite good, in fact, too good. So there's a need to filter out, so I'll show that as well. And then, some merging. If texts are clustered on the same location, the chances are great they belong together, so we group them. Yeah. And then it's just sent back to the MAM system. And then the MAM system, and here's where the value comes, the MAM system indexes the data and makes it available through search, filtering, faceted, etc. Yeah. So for the OCR part, we used Easy OCR from Jaded AI. It's really easy. So even my nephews and nieces can use it, in fact. So we had a coder dojo. I'm not sure if that's in other countries used. So to get children into developing code, and they use it. So it's really easy. It's ready to use, and it supports over 80 languages. So I'm not sure how many languages there are in Europe, but maybe 80 Irish dialects. I don't know. So let's look at an example. This is our MAM system with a lower third, person name, and his role. And because they're on the same location in the screen, we group them into one string of text and put it on a time code in a segment in the metadata. So if I want to find this person, I just can search on his name, and I immediately go to the time code where the person is in the picture. So that's the value. Okay, sounds too easy, so let's look at how it performs. So as I said, we use generic OCR. So we don't only detect person names, we detect all text. We store all the text, but we filter out the names. So in some cases we see that the algorithm is too good. So for example, and for our Dutch colleagues here, I have Sherin van Androoy here, and if you look at the raw detected OCR data, it looks like this. So yeah, that's not all relevant data, but it works quite good. Another example, so the raw OCR takes the subtitles, takes the picture in the background, so yeah, too much in fact. So there's a need to filter out the relevant data. In some other cases, we missed some things. So there was, for example, this one, the violinist. It looks like a clear text, but it only appeared about 2 seconds in the picture, and we had a minimum limit of 3 seconds. So yeah, we missed it. So sometimes too little data. To solve that, we had to tweak on the frame sampling and the grouping, etc. So yeah, I'll go into the filters in a minute, because that's where you go from raw, noisy data to real relevant data. And as I said, we also did some grouping, well, just to group the relevant data together based on location on the screen. So this is an example of the grouping. So this should have been the winner of Eurosong. So the raw OCR detection was the country, the title, etc., separately. And when we enable the grouping, it just detects this as one line of string, and you can have it in your data. But let's look at the filters we developed to get from noisy data to relevant data. The first one was the subtitles. So in still, a lot of our images have burned-in subtitles, and yeah, the OCR detects it as text. We have the subtitles also separately indexed in the MEM system, so there's no need to add them to the OCR detected. So subtitle filtering, let's check that. So the example of Turkey, the raw data recognized, and after the subtitles filter, the subtitles. So we trained the model to detect subtitles and just omit them out of the results. Then there were some small filters. The duration in screen I mentioned already. The length of the words after grouping. So for example, if you take Kim Jong-un, 3 words of less than 3 characters, if you apply this filter, 3 characters, it would have been omitted the results, but we group them as 1 word, Kim Jong-un, okay, 11 characters, and you keep it. So that's the filter based on word length, quite simple. Also on probability. So if the easy OCR detects some text and it gives you a probability of the correctness of the detected words. And we only set it at 50%. There was a question in the previous session about word error rate on speech transitions. So there we're talking about 80%, 90% for us. A probability of 50% was okay. But I'll talk about the lessons learned about this later. Yeah, but the most important filters are the 2 last ones. So I'll go to the heat map filter. So let's take a look. What is a heat map? Again, our cyclist with the rough data, the data filtered after word length, number of seconds in picture, etc. But what you see is we still have Shimano, Santini, etc., which is irrelevant for our use case. So how can we filter out these? What we do is we create a heat map. We take the entire content and we look everywhere where is there text in picture. And mostly these lower thirds are always placed on the same location. So if you go through an entire sequence, the places where the text always reoccurs is hotter, the heat map. So it goes from green, blue to red. And then from the heat map, we take a binary representation, and then only text visible in these yellow areas is retained. That's how we fixed the noise to this. So only Sherin van Androoy comes through, but as you see, we have still too much. We have one sponsor in the back who's also taken away. Also, that is one of the lessons learned I'll talk about. It's a matter of perception. Is that a bad thing, that there is the data freesia in the system? The the important thing is we can find this person if we want to find it. So, okay, but still again, we just have text. We don't know if it's really a name yet. So some colleagues talked about thesauri, etc. So we also tried to filter out names. How we did that? We first tried to use our own thesauri, but they're not really accessible. And not to lose too many time on it, we took an open model, and that's Flair. So it's it's a model trained for Dutch names, but it works for international names as well. And that's just you give the model a text, and he says this part is a name with a probability of about that much percentage. And then this is the result. So from the entire detected text sequence, we retain only those names, and it works quite good. But at what cost? So cost in time, money, and time won on not doing it manually anymore. So, but on average, the algorithm, though the entire sequence of uploading, cutting it up into blocks, sampling, doing the OCR detection, well, it's for a 40-minute clip, it's 25 minutes total. So even with parallel processing on a powerful cluster on AWS. But you can play with some parameters to get the cost down or get it even faster. We did a frame sampling of 1 per 25, so just every second we take a frame. If we want higher accuracy, you could take more frames, but then it will take longer and cost you more. So it's, yeah, you have to play around with these parameters. And but without parallel processing, it can take hours. So you really need a good cluster. So we used a cluster of, well, it's a shared cluster. So for this application, we just used 5 servers in the cluster, 8 cores each. We also use it for other applications like the segmentation or facial recognition. So yeah. And yeah, if you go up in frame sampling, the processing time will also go up. So it's a trade-off. Yeah. Okay, then some lesson learned. The first question my manager asked me, he asked me, was it worth it? In my mind, yes. We don't have to rewatch and scroll to all our footage again to have the text recovered, so that's a big plus. If you want to do this, I would suggest to do it with a generic OCR model. Don't train on specific graphics, because these change all the time. And then, yeah, to keep the cost manageable, play around with these parameters. And like the one example we shown, there will be misses and there will be noise. It's something you must accept because that's sometimes difficult for passionate people to accept faults. And the last thing is you really need a human in the loop. We didn't build an automatic machine learning loop, so there's always manual testing, feedback to the developers, and they retrain the model, and so it's not an automatic learning, but we do it in an iterative way. And yeah, just talk to my colleagues how they perceive the project in the break, and thanks very much.